Hi everybody, this is Emilio again, and today I will talk with industrial communication expert Tobias Drexel about CAN Fieldbus networks. We'll give you detailed insight on remote diagnostics and troubleshooting of CAN bus lines. In this session, you'll learn the fundamentals of CAN, common challenges including signal errors, device malfunctions, and communication breakdowns. And of course, we'll offer powerful diagnostic techniques and proven strategies for remote maintenance and troubleshooting using the latest tools and methodologies. Watch now. For the beginning, let's start with some CAN basics. Can you explain to us what CAN is and what it is used for?
Controller Area Network is a communication technology widely used in industrial and automotive applications. It allows various devices to exchange data efficiently. All CAN nodes are connected in parallel using a twisted pair consisting of CAN high and CAN low signals. The CAN ground is recommended but not mandatory. A CAN message primarily consists of the identifier, which defines the priority of the message and the type of data being transmitted. It further contains the control field, which includes information about the length of the data. After that, the data field carries up to 8 bytes of payload. And finally, there's the CRC, or cyclic redundancy check, which is being used to ensure the integrity of the message data. Additional fields include the acknowledge field and the end of frame markers that mark the actual end of the message. This structure allows for a robust and efficient data exchange in automotive and industrial applications. However, like any system, CAN can experience some problems. Remote diagnostics and troubleshooting become crucial, especially when dealing with these networks in complex or geographically dispersed systems. Quickly identifying and resolving the issues can minimize downtime and ensure a smooth operation of the network.
Now let's focus on some common physical failures that occur within CAN networks. Tobias, could you give us some introduction on some of these frequent issues?
Yeah, for sure, Emilio. One of the major issues is the improper network topology, such as exceeding the maximum bus length or using too long cable stubs, which then disrupt the network's functionality. A poorly designed topology, like having the cable stubs too long or the bus line too long, can lead to signal reflections. These reflections then can cause instability of the network communication. Typically, the bus should be kept as a continuous line with the stubs as short as possible to avoid exactly these issues.
And what about the wiring issues? What should our viewers look out for?
In terms of wiring issues, the issues often stem from quite simple mistakes, like having a shortcut or incorrect wiring connections. It's crucial to ensure that the CAN high is connected to CAN high, CAN low to CAN low, and so on. Also, it's important to use the recommended cable diameter for the used bus length. That's important to ensure the signal integrity. Additionally, electrical issues can vary, but from our point of view, they most often stem from an improper grounding concept. It's important to avoid ground loops. This can be done by ensuring that CAN ground is properly connected to the ground line at multiple points, which is our recommendation, especially when the ground level is not stable.
And what about electromagnetic compatibility? How does EMC problems manifest in the CAN network?
EMC problems are typically due to electrical disturbances or inadequate shielding of the network. CAN lines must be properly shielded against external electromagnetic influences, and it's important to ground the shielding on one side of the bus to prevent ground loops. Also, having a defect transceiver or bad signal quality can drastically reduce the network stability. Tools like the Ixxat CAN check are useful to check the voltage levels of the CAN signals to ensure that they are within the expected ranges.
Could exceeding the number of connected CAN nodes cause issues?
Yeah, absolutely. Each transceiver has a limit of how many nodes it can handle. Exceeding this number can degrade the network's performance. If necessary, segmenting the network using repeaters or bridges can help to manage this. Lastly, the capacitive load can cause physical failure on the CAN bus. for example when suppressor circuits are used within the system.
Let's dive into the logical challenges that arise within software applications. Tobias, what are some of the typical logical issues that occur within a CAN network?
Basically, 4 major types of issues can be identified. The first and most common issue is that multiple CAN nodes transmit messages using the same CAN identifier. This leads to message collisions and thus communication failures. In CAN networks, it's essential that a CAN identifier is only used uniquely, so that messages are properly recognized and routed within the system. It's crucial during the design phase to assign unique identifiers to each node and ensure that these assignments are rigorously documented and implemented. Regular audits of the network configuration can help to catch these errors already during the design phase of the network. The second point is errors that occur in the implementation of the software. They often occur in the upper layers of the network protocol, especially in the OC layer 7, called application layer. An incorrect implementation here, especially in systems like CAN open modules, can disrupt the entire communication process. It's important to ensure that the software adheres to the specifications of the CAN protocol being used. Third issue is the output of incorrect values in the system. This is usually caused by faulty or damaged devices within the network. For example, if a sensor is malfunctioning, it might send incorrect data, which could lead to erroneous operation. It's important to regularly check the health of each device in the network and replace or repair it if necessary. And the last point, the fourth point, is in terms of the bus load. The CAN specification recommends to not exceed 65% of bus load to ensure a smooth operation. More conservative recommendations advise you to not go more than 40% of bus load. A high bus load can slow down the entire network and thus increase the risk of data collisions and transmission errors. Monitoring tools can be used to check the bus load and ensure that it is within safe limits.
Moving into more technical aspects, Tobias, could you explain how proper CAN diagnosis is normally conducted?
Yeah, for sure. A thorough CAN diagnosis starts with a detailed description of the problem to determine whether it's a hardware or software problem. If there are no CAN error frames, the next step would be to do a trace file analysis of the network to identify any anomalies there.
And if there are error frames present?
If there are error frames, they usually indicate that there's a problem within the physical layer. The standard approach of troubleshooting starts with examining the bus medium and then working towards the upper layers, towards the application layer. Here's a step-by-step breakdown. In the first step, you should do a visual inspection and topology check. This includes to check the network topology to ensure it's set up correctly, to ensure that there are no obvious physical damages or misconfigurations. Second, there's the wiring test. You should check the wiring, including the topology, cable integrity, and termination, to ensure that everything is connected properly and according to the specification. The next step, number 3, is a functional test. There you check the system's functionality to see if the problem is reproducible, sporadic, periodic, or a permanent problem. Number 4 is the error frame analysis. This involves checking for physical issues, incorrect CAN baud rate settings, or missing acknowledgements that might cause error frames. Number 5 is a signal quality check. We can assess the CAN signal levels, the abruptness of lengths, signal reflections, electrical disturbances, or common mode issues to gauge the integrity of data transmission. And the last step finally is to do a recording and a trace file analysis. You can tools like CAN open or CAN open trace applications to record and then analyze the network activity to pinpoint where the issue is exactly occurring.
That sounds like a comprehensive approach. How do you typically narrow down the potential causes?
By following the step-by-step breakdown, you can isolate the problem area quite exactly. Once isolated, we can apply targeted fixes, and after this we continuously monitor whether the issue is really solved to prevent any future disruptions.
So, Tobias, when CAN error frames appear on the Fieldbus line, what is the typical problem that might cause them?
One of the main reasons for them is an improper network topology. The CAN bus has to be implemented as a continuous line. Cable stubs should be avoided as much as possible, but are inevitable when nodes are connected. Up to a certain length, the signal reflections caused by cable stubs do not affect the transmission stability because they dissipate before the time of network sampling. The following formula can be used to approximately calculate the maximum stub length. It should be less than 5% of the maximum length of the bus system. Depending on the baud rate, if longer stubs are needed, the network must be segmented using CAN repeaters, bridges or gateways. The bus must be terminated at its most distant ends with a 120 ohm resistor between the CAN high and CAN low signal lines. The resulting resistance between CAN high and CAN low is thus 60 ohms. If the bus is segmented using CAN repeaters, bridges or gateways, also the new segments must be terminated correctly. Because of the arbitration and acknowledgement mechanisms used with CAN or CAN-FD, the maximum bus length is limited and decreases with increasing bit rate. Besides the pure cable length, also the use of electrically isolated bus interfaces shortens the maximum possible bus length, since such interfaces have to be treated like having additional cable length of 10 meters. The use of a CAN repeater with electrical isolation furthermore reduces the maximum possible bus length by 30 meters. This is also caused by its internal logic. If the maximum length is exceeded, the bus must be segmented using CAN bridges or gateways. CAN repeaters cannot be used in this case since they transmit the bus signal directly. This means that the segments connected with the repeaters have to be counted as part of the main bus in terms of signaling purposes. And by the way, using a CAN repeater, you can also create star topologies that changes the CAN bus length.
As we dive deeper into the specifics of CAN network issues, could you explain the common problems with wiring?
Yeah, for sure. In CAN networks, the issues usually originate from shorts or incorrect wiring of CAN high, CAN low and CAN ground signal lines. It's essential to check that CAN high is connected to CAN high, CAN low to CAN low and CAN ground to CAN ground, and avoid any mismatches in regards of this. This could always lead to network failures. Another important topic is the used cable diameter. It should be based on the bus length that is being used. For instance, an AWG22 cable is suitable for up to 100 meters, AWG20 for up to 250 meters, and finally AWG18 for up to 500 meters. Also ensuring that the connectors are not oxidized and make a good contact is essential for reliable connections. As well, network errors often occur when the termination resistors are missing or have been placed incorrectly.
Moving on to electrical problems. What should network managers watch out for?
Yeah, in terms of electrical issues, they often stem from grounding problems. Using the CAN ground wire appropriately is vital if the ground is not stable. It should not be connected to the ground at multiple points to avoid any ground loops. Ensuring good grounding quality, especially for devices like frequency converters, is crucial. Additionally, EMC issues arise from electrical disturbances and poor shielding. CAN signal lines should be shielded against external electromagnetic influences, and the shielding should be connected across several line sections. Importantly, to avoid creating ground loops, the shielding should only be grounded on one side of the bus. Another way of avoiding is to use CAN bridges or CAN repeaters having a huge galvanic isolation. Issues at the bus interface, like a defect transceiver or poor signal quality, can significantly disrupt the communication. Using tools like the Ixxat CAN check to assure that the voltage levels and the recessive and dominant CAN signals are correct can diagnose these problems effectively.
Can you expand on the problems caused by exceeding the numbers of connected CAN nodes?
Yeah, for sure. Each CAN transceiver has a limit of how many nodes it can handle. Generally up to 100 per segment should be no problem, though this can vary based on the specific type of transceiver being used. Exceeding this number can overload the network, requiring network segmentation with repeaters or gateways to maintain the system stability. Lastly, a high capacitive load within the network can degrade the quality of the CAN signals, making them less rectangular and more prone to errors. This can often be mitigated by splitting the CAN network into several segments by using devices like a CAN repeater or a CAN bridge to minimize the effects of the capacitive load.
It seems having the right tools for testing and diagnosis is essential. Could you remind us in particular what kind of tools that are used for this?
Tools like the CAN Analyzer V3 are great for tracing down errors and do a frame analysis. The CAN check is used for wiring checks and an assessment of the signal levels. And an oscilloscope is invaluable when having a detailed look at the signal levels, flanks, reflections, and disturbances.
All right, thank you. Now let's talk about CAN troubleshooting without using CAN error frames. So if a network isn't showing any CAN error frames, how can I still analyze it and troubleshoot it?
Even without error frames, tools like a CAN Analyzer equipped with a CAN Open module are invaluable. They allow us to check the network's messages, heartbeats, and responses to ensure that all the nodes are communicating correctly.
And what kind of issues can I uncover in this way?
Using this methodology, you can identify several logical issues. The first one are identifier collisions. The CAN specification requires you that different nodes must not transmit any messages with the same identifier to prevent collisions. Secondly, there are implementation errors in terms of the software. Problems can arise, for example, when having CAN Open modules that are not correctly implemented according to the standards. This can lead to significant issues and communication errors. The third point is you can detect incorrect data values. Damaged devices like sensors can send incorrect data values in the network, which then could lead to a faulty operation of the network. And the last point is exceeding the maximum bus load. The CAN standard requires you to not have a bus load bigger than 65%, with more conservative recommendations suggesting to keep it less than 40% to ensure a smooth network operation and prevent any network congestions.
So, more specifically, how do these tools help with these issues?
These tools, especially when equipped with the right modules, can monitor all the traffic in the network, allowing us in real time to see all the data transmissions and assess whether the nodes are operating within the specified parameters. By analyzing the patterns and timing of the messages, we can identify any anomalies that suggest an underlying problem, even without explicit error frames in the network.
This seems like a proactive way to maintain network health, right?
Yeah, absolutely, Emilio. Regular monitoring with these tools can preemptively identify issues before they escalate into more significant problems, greatly reducing potential downtime and ensuring the network runs efficiently.
Let's move forward. Tobias, could you share how the reliability of a CAN network can be maximized right from the start?
Yeah, for sure, Emilio. To ensure a high reliability in the CAN network, this involves several key practices such as the usage of standard shielded CAN cables. It's crucial to use these CAN cables with a 120 ohm impedance. This helps to minimize the noise and interference within the network. The cable should be a twisted pair type to reduce the influences of electromagnetic issues. Secondly, the adherence to the CAN line topology is important. Implementing a linear topology without unnecessary deviations and stubs helps to maintain the signal integrity across the network. Additionally, a correct placement of the CAN termination resistors is crucial. The termination resistors are vital for preventing signal reflections at the ends of the networks. They should be correctly placed to ensure the network's impedance is properly matched. And finally, a proper wiring is key to ensure maximum reliability. Using the correct wires for CAN high, CAN low, and CAN ground is essential to ensure the system's electrical stability.
So, how does galvanic isolation play into all of this?
Galvanic isolation is particularly important within environments with high electromagnetic interferences. By using devices like the Ixxat CAN repeaters or CAN bridge, you can isolate, for example, frequency converters from the rest of the network, which helps to prevent noise and ensures cleaner signal transmissions.
And how about managing capacitive loads?
When you have high capacitive loads that can dampen the signal edges and degrade the signal quality, you can segment the network using CAN bridges repeaters, like those from Ixxat. This segmentation not only manages the capacitive load, but also improves the overall signal quality across the network. Another effective method is to reduce overall capacitance by splitting it into several segments.
And if there's a need to extend the bus beyond the standard length?
When you have the case that you want to exceed the maximum bus length, you can use a CAN bridge as a solution. It allows to extend the network while maintaining the signal integrity, effectively increasing the operational performance without degrading anything.
Tobias, given the complexities of CAN networks, are there more proactive approaches that can help minimize the downtime?
Yeah, for sure, Emilio. A very effective way is to continuously monitor the network, and one of the best tools for this is the Ixxat CANnet in the VCI mode. This allows a network manager to continuously monitor error frames across the CAN network.
So, in practical terms, how does that help?
When you have the CANnet in VCI mode attached to the network, you can continuously observe and log all the activities on the CAN networks, particularly looking out for error frames. This constant surveillance helps to quickly identify and diagnose any issues before they have a big impact and lead to a significant downtime. It's all about catching the errors as early as possible and addressing them promptly. This approach not only helps maintaining the stability of the network, but also significantly reduces the potential for prolonged disruptions that can arise from unresolved network issues.
Thank you, Toby. This discussion on CAN network monitoring has certainly demonstrated the importance of proactive approaches in reducing downtime and maintaining system health. Your expertise is indispensable to anyone looking to optimize their CAN network operations. Thanks everybody for watching, and have a nice day.